In this problem, we're trying to determine the reactions at point A and point B that will maintain static equilibrium in this system. So we're looking to find reactions at A and B. So we are going to need to make a free body diagram for this two-dimensional rigid body. So we need to choose the object that we want to isolate. So here, since we need to know the reactions at A and B, the pin itself at A cannot be included in our object because we need to see what the pin does to the object. And this bar from B to C cannot be included because we need to know what the bar does to the remaining object at B. So our free body diagram in this case will be the object is going to be the wooden piece that goes from A to B to the end. So that is going to be our object of interest. I need to establish my coordinate system here. So now that's my object. Now I need to include all of the forces, whether it be applied forces or reaction forces, that are going to act on my object. I'm going to start by just copying exactly the external forces that act on my object. So at the end here, I have this 800 Newton applied force. And I also have this couple 900 Newton meters. I copy those exactly. The 900 is clockwise, the 800 is down. And I also have this applied force over here of 600 newtons. And I'll need to start to put some dimensions down. So that's going to be 1 meter, and 2 meters to go from A to B to the end there. So I've accounted for all of the applied forces. Now I can put in my reaction forces. So I'll start at A. I have a pin connection. So what the pin is going to do is, from the object I'm keeping, I cannot move it left or right. The pin is preventing that. I cannot not move it up or down, and I cannot move it anywhere in the XY plane. So the pin is preventing all translation. So I'm going to model that as a horizontal component I will call AX, and a vertical component I will call AY, are the two components of force that the pin is exerting on my object. However, the pin does allow rotation around point A. I'm being told to treat it like a pin, so that means that I can rotate it at least a little bit around point A. And when I'm considering what reactions I'm going to have, I'm ignoring that it's connected at B when I'm doing this assessment. I'm just saying A in isolation is preventing all rotation, all translation, but it would allow rotation. Now we're going to move on and look at B. So at B, I'm pinned to this two-force strut. So like a cable or like a rope, the force in this strut is going to be along its axis, which means that the strut is exerting a force from B to C, or possibly C to B. It could be tension, it could be compression. I'm going to assume it's in tension though. And that will be the force in BC. And this is my point B, and this is my point A. And I need to know, I know the direction that BC is pointing because I know for a two-force member, it's going to be along its length or along its axis. So if I look, the triangle ABC is actually a 3-4 triangle in disguise, a 3-4-5 triangle in disguise, because if I double all the sides, I'm going to get 3 from A to C and 4 to A to B, making B to C, at least by ratio, 5. So for my dimensions or for the angle of this, I can put in a ratio triangle that's a 3-4-5. I could have done this with an angle, that would have been fine, or coordinates, but this is going to get that same point across. So now I'm ready for my equilibrium equations. Taking a quick look at my free body diagram, I have AX and AY at what I'm calling FBC. Point A, point B are on this diagram, so in my find step, I want the reactions. I will be able to find them from this free body diagram. So let's start writing equations. I'll start with my force equations. X, just out of habit, I'll look at first. And looking at my free body diagram, I assumed AX was to the right, so that's going to be positive in this equation. AY is up, so it will not be here. 600 is down, 800 is down, and the 900 Newton meters is a moment, so it will not appear in my force equations. So the only other force that has an X component is the X component of FBC. So that's going to be minus 4/5 FBC. So I have one equation, but I have two unknowns in it, so I'm going to wait to try to solve anything, because oftentimes, especially when we get the moment equation, we will probably, in 2 dimensions, be able to write an equation that has only one unknown in it. So it's going to make that solve step easier. Typically, if we hold off until that's the case, worst case scenario, we're going to show that we have a solvable system that we just have to then solve once we have the whole thing written out. So in the y direction, I will have my unknown AY up, minus 3/5 FBC. FBC is pointing into the third quadrant, so it has negative x, negative y. And I have a bunch of these applied forces. I have 600 newtons down and 800 newtons down as well. So between equations 1 and 2, I have 3 unknowns, but only 2 equations. So I'm going to move on to my third equation, where I'm going to do now a moment about a point of my choosing. Looking at my free body diagram, the rule of thumb is choose a pin if there's a pin in your picture. So in this case, I do have a pin at A, and I'm going to therefore desire to put my moment, or find the moment around A and see what makes it 0. Again, I can choose any point. I could choose B, I could choose the end, and I'm still going to get an equation that is going to give me my answer. But by selecting A, because AX and AY both have their lines of action pass through A, we don't include them in this equation, which means that this equation will already not have 2 of the variables in it that I don't know, AX and AY. So let's see what is left. So AX, AY are not there. I'll move left to right. The 600 Newton force is going to be acting 1 meter away. So force times distance from the 600 newtons, and around point A, that is going to be causing a clockwise or negative moment. Right? So again, we are going to assume counterclockwise positive when we do these typically. So that is clockwise, so it's negative. Right? Moving to the right, we'll have FBC. If we look at that, its horizontal line of action passes through point A, so we don't need to include that. If I broke this down, just for illustration, I have the horizontal part of it, and I have the vertical part of it. So the horizontal part, line of action passes through A, we don't need to include it, but the vertical part we do. So the vertical part is going to be its 3/5 times FBC times its perpendicular distance to A is 2 meters. Right, so the vertical part is 2 meters away because we're using the perpendicular distance. So to that point, again, this would be the vertical part of FBC. It is located 2 meters away from A. That's its perpendicular distance. The perpendicular distance of the horizontal part would be 0, and that's why it's not being included. All right, so that is, again, a force times a distance. The 3/5 FBC is the force, the 2 is the distance. That is going to be causing a clockwise or negative moment around point A. Okay, I also have, I didn't account for it yet, is the 800 Newton force. And its perpendicular distance to A is 4. 800 is vertical, so I'm using the perpendicular distance, which is the horizontal distance. That too is a negative moment that's going to cause around A. Right, so I've accounted for AX and AY, they were 0, the 600, the vertical part of FBC, the 800. So finally, I need to account for the 900 Newton meter couple. So this is where it gets included. Right? And I include that as negative 900. I'll put it on the next line here. It's negative because it is clockwise, and we've established counterclockwise to be our positive direction. And note, it's just that negative 900. I don't multiply it by any distance. It is already a couple. So that has already been accounted for. So these are the 4 things that are going to be in my equation 3. Looking at the equation 3, because I was strategic and I chose to take the moment around point A, the only unknown in equation 3 is FBC. So I'm going to start by solving for FBC. One equation, one unknown. We can do that by hand, and if we do, we find that FBC is a negative 3920, and we're in newtons. So it turns out that BC is actually in compression. For simplicity, for consistency, I assumed tension in the way I drew it. I got a negative answer, so it turned out my assumption was wrong. It's actually compression. So that's okay, as long as I'm consistent with it. So notice when I wrote my equilibrium equations, everything was written premised on FBC pointing down and to the left, which I've now numerically shown was not the case. But as long as I'm wrong consistently, that's going to be fine. So I'm going to still use this negative 3920 when I go into, let's say, equation 1 next. Right, so I have AX, I have 0 equals AX minus 4/5 times negative 3920. So that negative will carry through when I substitute it into equation 1. And that will tell me my AX value. And I will get negative 3130 newtons out of that. All right, so here, for FBC, because it was a tensile or compressive force, the negative told me compression. For like a reaction like a pin, the negative sign is telling me that basically the same idea, that my assumption of direction was wrong. However, for a reaction force from a pin or from a couple, it does not tell me it's in compression. It's just telling me the direction of it. I assumed it was to the right, but it's actually pointing to the left. So the reason I'm putting like the compression or pointing to the left here is this is physically what it is doing. This inference is independent of whatever my assumption was. I would still make the inference, even if I assumed AX was to the left, I would then get a positive answer, which would then affirm my assumption of AX being to the left. But no matter what I did, I would get left as the real world physical interpretation of the direction of AX. And then I can go into equation 2, again using FBC, and now I can solve for AY. Right, putting that value of negative 3920 in and solving for AY, I will get that AY is a negative 950 newtons. I assumed it was up. I got a negative, meaning my assumption was the opposite of what was actually the case, and it's actually down. So it turned out in this one, actually, all of my assumptions were incorrect, but that's all right. I got the right numerical value or the right magnitudes for everything, and I have made my inference that FBC is going to be in compression, AX is going to be exerting a force to the left on my object, and AY is going to be exerting a force down on my object. So I found what I was asked to find, the reactions at A and at B. And again, as a note, for the moment equation, which I, in this case, happened to do last, I selected point A to take the moment about, and that gave me the benefit of making the algebra and the arithmetic easy to solve in this one by solving equation 3 first for my one unknown, using that result to find my other two unknowns, one equation at a time.